Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to discuss spans and subspaces. So in this topic, we will review the definition of the span of a collection of vectors. We will discuss when we can and cannot remove a vector from a collection and yet leave the span of that collection unchanged. We'll see an algorithm for minimizing the number of vectors in a collection while leaving the span unchanged, and describe how we can determine when the spans of two different collections of vectors are equal. Now, recall the definition of the span of a collection of vectors. The span of a collection of vectors u1 through un is the set of all linear combinations of these n vectors. We denote the span of a collection of vectors using the notation span with the vectors within braces. Note that the span of no vectors is the zero vector. Again, this is similar to the sum of no numbers being zero. Now, if v is in the span of a collection of vectors, we will write that as follows, where we can read this either as v is in the span of u1 through un, or v is an element of the span of u1 through un. Similarly, if v is not in the span of a collection of vectors, we will use the same symbol but have a slash through it, indicating not. And again, we may read this as v is not in the span of u1 through un, or v is not an element of the span of u1 through un. Now, note that v being in the span of a collection of vectors is true if and only if there exists at least one solution to there being a linear combination of the vectors u1 through un that equals this vector v. And this is true if and only if v depends on u1 through un. Again, note that the zero vector is in every span, as there is always at least one solution to finding a linear combination of vectors equaling the zero vector. Thus, the zero vector depends on any collection of vectors, including none. Now, a few observations. The span of any collection of vectors is a subspace of the vector space from which the vectors come from. In either r to the n or c to the n, every subspace is the span of a finite collection of vectors, and we will prove this in time. In other vector spaces, this is not necessarily the case. For example, consider the subspace of all bounded discrete time signals. There is no finite collection of discrete time signals such that the span of that collection is the collection of all bounded discrete time signals. Now, here's a nice little theorem. Suppose that we have the span of a collection of vectors u1 through un. However, there is a specific vector in that collection u sub k that is in the span of the balance of the vectors. In this case, the span of all the vectors except for the vector u sub k is still equal to the span of all n vectors. Proof. Well, suppose v is an arbitrary vector within the span of u1 through un, and let us assume that u sub k is in the span of all other vectors, u1 through un, without u sub k. Well, in this case, we must be able to write v as a linear combination of the vectors from u1 through un, And we must be able to write u sub k as a linear combination of all other vectors u1 through un, ignoring u sub k. Well, if that's the case, then we can substitute the second formula into the first. And we note that we can replace u sub k with its linear combination of all other vectors within the collection u1 through un, again excluding u sub k. All right. Well, notice now that we can multiply that inner sum of products by alpha k, and then using the properties of vector scalar multiplication and vector addition, we can regroup this to see that v must therefore also be dependent on all vectors other than u sub k. And we can explicitly find these coefficients as well. So therefore, v must also be in the span of all vectors from u1 through un, excluding u sub k. Thus, the span of the smaller set of vectors must equal the span of the larger set. Again, only if, in this case, u sub k can be written as a linear combination of other vectors. Now here's a complementary theorem. Given a collection of vectors u1 through un, if there is a vector in this collection u sub k that is linearly independent of the other vectors, then the span of the vectors not including u sub k is a strict subspace of the span of the n vectors. You will recall that a strict subspace is a subspace that is not equal to it. So, therefore, the span of all vectors not including u sub k must be a smaller subspace that is inside of the span of all n vectors. Proof. First of all, the span of any collection of vectors is a subspace. So the span of the larger and smaller sets of vectors, they are both subspaces. Also, every vector in the span of the smaller set not including u sub k must be in the span including u sub k. Why is that? Well, if it's in the first set, then we can write it as a linear combination of all vectors other than u sub k. Well, if this is true, then we can also write it as a linear combination of all vectors including u sub k, as all we need do is multiply u sub k by 0, and we get the same result. However, u sub k is independent of the other vectors. So, therefore, by definition, u sub k cannot be in the span of the other vectors. So, therefore, there is at least one vector in the span of the smaller set that is not in the span of the larger set. Thus, the span of the smaller collection of vectors must be a strict subspace of the span of the larger collection. Thus, if we have any collection of vectors u1 through un and one of the vectors is dependent on the others, then we may remove it from the collection and the span is unchanged. Also, if any vector is independent of the others, we cannot remove it from the collection without changing the span. So, for example, let us consider the span of these 5 vectors. Now, we immediately note that this collection must be linearly dependent. After all, we have 5 vectors in R3. and the maximum rank of the matrix that has each of these vectors as columns is 3. Now, from before, we saw that the matrix on the left, that is, the matrix with columns comprising the 5 vectors, we saw this matrix is row equivalent to the matrix on the right. Therefore, the rank of the matrix is 2. Thus, there are 3 variables associated with columns 2, 4, and 5. Now, if we focus only on the first 2 columns, therefore, so exclude columns 3, 4, and 5, note that the augmented matrix on the left is row equivalent to the augmented matrix on the right, and therefore there exists a unique solution. Basically, we can write the second vector as 2 times the vector plus 0 times each subsequent vector. Therefore, the second vector linearly depends on the other 4. Thus, the span of the 5 vectors must be equal to the span of the first, third, fourth, and fifth vectors. Again, taking a look at this matrix and its row equivalent matrix in row echelon form, we notice that column 4 is associated with a free variable. Thus, let's take columns 1, 3, and 4. So again, taking columns 1, 3, and 4 from the matrix on the left, if we were to do Gaussian elimination on that matrix, we would get exactly columns 1, 3, and 4 of the matrix on the right. We don't have to do any other work. We've already done the Gaussian elimination. Consequently, we note that the rank of the 3 by 2 matrix is equal to the rank of the augmented matrix, and thus the target vector can be written as a linear combination of columns 1 and 3 of the original matrix in the top left. Thus, once again, the fourth vector in the original set can be written as a linear combination of the first, third, and fifth vector, where we just multiply the fifth vector by 0. Alright, so this now says that the fourth vector in the original collection depends on the first and third and also the fifth vector. Thus, we can indicate now that the span of the original collection of vectors is equal to the span of the first, third, and last vectors, because we were now able to first exclude the second vector and now the fourth vector. Finally, once again, taking a look at the row echelon form matrix, if we take columns 1, 3, and 5 in both matrices, we see that, oh, wait a second, we can once again write the fifth vector in the original set as a linear combination of the first and third. All right. Well, that's nice, because now that means that the fifth vector also depends on the first and third vectors. Thus, finally we see that vectors 2, 4, and 5 linearly depended on vectors 1 and 3, and therefore the span of all 5 vectors here equals the span of the first and third vectors. Now, once again, from the original matrix and its row equivalent matrix in row echelon form, we note that if we take columns 1 and 3, we see that the matrix comprised of the column vector 1 and the third vector is row equivalent to a matrix with rank 2, and therefore we may conclude that these two vectors are linearly independent. We can no longer remove one of these vectors from the span and get the same original span. The span of any one of these vectors, which essentially is all scalar multiples of that vector, is a strict subspace of the span of these two vectors, which incidentally forms a plane in R3, and that plane must go through the origin. We can also proceed as follows. Given these 5 vectors here, we can create the matrix that has these 5 vectors as columns, and then we can find the row equivalent matrix that is in row echelon form. From that row equivalent row echelon form matrix, we note that columns 2, 4, and 5 would be associated with free variables. Thus, strike those 3 vectors out from the original collection. Thus, we now know 2 things. First, we know that the span of the 5 vectors equals the span of the 2 remaining vectors, but not only that, we know that the remaining 2 vectors are linearly independent of each other. Now, suppose we have the spans of 2 collections of vectors. How do we know if these 2 spans are equal? Well, if you know nothing about these collections, you must test whether or not each vk is in the span of the vectors u1 through um for each k going from 1 to n, and you must check if each uk is in the span of the vectors v1 through vn for all vectors k going from 1 to m. That is, you essentially have to attempt to solve vk as a linear combination of the vectors u1 through um for each k going from 1 to n, and you must try to solve for uk equaling a linear combination of the vectors v1 through vn for all vectors k going from 1 to m. Fortunately, as soon as you find that one of these systems of linear equations has no solutions, you may stop. The spans are not equal. If, however, you get to the end, then you know that the span of the first collection of vectors equals the span of the second collection of vectors. So, following this topic, you now have a reinforced understanding of the span of a collection of vectors. You know that the membership of a vector in a span is equivalent to dependence of that vector on that collection, which is equivalent to being able to solve for that vector as a linear combination of the vectors in the collection. Also, given the span of a collection of vectors, if one vector linearly depends on the others, we can remove it and the span is unchanged, while if one vector is linearly independent of the other, we cannot remove it without changing the span. Finally, determining if the spans of 2 collections are equal requires us to check if each vector in one collection is in the span of the other. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!